In this video, I am going to bring forward some of the fundamental concepts of galvanic cells. This video is designed as a recap for the TYBSc students and as a course material for the SYBSc students of St. Xavier's College in particular and Mumbai University in general. Now first of all, what is a galvanic cell? I am sure you all have studied in the lower classes that galvanic cell is a cell in which chemical energy is converted into electrical energy. So a voltaic cell or a galvanic cell is an electrochemical cell in which a spontaneous reaction generates an electrical current. Other way around, if electricity or current is passed through a solution and it brings about a reaction, then it is called an electrolytic cell. So basically in an electrolytic cell, an electric current drives a non-spontaneous reaction. Now, any voltaic cell or galvanic cell consists of two half cells. These two half cells are externally connected with the help of a wire in order to allow the flow of electrons from one half cell or one electrode to the other. Whereas the two cells are internally connected using a Saul bridge which allows the flow of ions from one half cell to the other or from one electrode to the other. So as you all can see out here, there are two half cells. One is involving a zinc rod dipped in a solution of zinc sulfate. The other one is a copper rod dipped in a solution of copper sulfate. The two cells are connected externally using this particular wire and internally with the help of a Saul bridge out here. At this particular zinc electrode, the zinc atoms on the rod get converted into zinc ions and these zinc ions pass off into the solution and the two electrons which are released are left behind on the rod itself. As a consequence, the zinc rod will get a negative charge. So basically the zinc rod becomes electron rich. This reaction is an oxidation reaction and therefore this electrode qualifies to be the anode, as at anode oxidation reaction takes place. So basic definition of an anode, it is an electrode at which oxidation reaction takes place. Whereas at the copper electrode, the copper ions from the solution gain two electrons from the copper rod itself and get converted into copper atoms. These copper atoms obviously will go and stick to the copper rod, and as a consequence the weight of the copper rod will increase with time. Now this reaction is a reduction reaction and therefore we call the copper electrode as the cathode. This is because fundamentally cathode is defined as an electrode where reduction reaction takes place. Now what does a Saul bridge exactly do? So Saul bridge is a tube of electrolyte in a gel that is connected to the two half cells of the voltaic cell, and it allows a flow of ions but prevents the mixing of the different solutions that would allow direct reaction of the cell reactants. So in a Saul bridge, the cations will obviously move to the cathode whereas the anions will move to the anode. So let's go back to the diagram. You all can see out here that the Saul bridge is filled up with an electrolyte. The electrolyte generally used is KCl. So as it is marked out here, K plus ions are moving to the cathode whereas the Cl minus ions are moving to the anode. So if you look at this overall structure, zinc being electron rich sends out electrons to the electron deficient copper cathode externally. However, to complete the circuit, some negative species will have to move from the copper side to the zinc side, and this is done by the chloride ions of KCl present in the Saul bridge. So chloride ions will move from the copper electrode to the zinc electrode. Also there is one more utility of the Saul bridge, and that is to minimize the liquid junction potential. So basically in a galvanic cell or a voltaic cell, the electrode at which oxidation takes place is the anode, the electrode at which the reduction takes place is the cathode, and electrons flow in the external circuit obviously from the electron rich anode to the electron deficient cathode. So basically anode is a negative electrode and cathode is a positive electrode. Also at this point I would like to remind you that the zinc electrode, as you all can see out here, loses weight with time, whereas the copper electrode out here gains weight with time. This is because the zinc atoms on the rod pass off into the solution as zinc ions, leaving behind the electrons on the rod and thus making the rod electron rich or negative. Whereas the copper rod becomes heavy as the copper ions from the solution go to the copper rod, absorb 2 electrons as shown out here and become copper atom. Obviously electrons are being consumed in this process from the rod, and as a consequence the rod becomes electron deficient or positive. Now if the zinc rod and copper rod are therefore connected externally with the help of a wire, then electrons will flow from zinc to copper. However, the conventional current, as we know, flows from positive to negative, and hence the conventional current will flow from copper electrode to zinc electrode. If we place a small bulb in the circuit, then due to the flow of current, the bulb is going to glow. So I'll repeat once more. At the zinc electrode, the zinc atoms from the rod pass off into the solution as zinc ions, leaving behind 2 electrons on the rod. Whereas at the copper electrode, the copper ions go to the copper rod, take up 2 electrons and get converted into copper atoms. If we add up the 2 reactions that we saw right now, then the overall cell reaction can be written as zinc atoms plus copper ions, giving you copper atoms plus zinc ions. The cell can be represented as zinc stroke zinc ions. Say the concentration of zinc ions is 1 mole per liter. So then that is represented in the brackets or parentheses out here. There is a salt bridge out here which is indicated by 2 vertical lines. The copper ion solution is represented out here. Again, let's assume that the concentration of copper sulfate was 1 mole per liter, and the copper sulfate solution is different in phase from the copper rod, and the copper rod is represented out here. So the anode is represented to the left, whereas the cathode is represented on the right. The salt bridge separating the 2 solutions is represented by a double vertical line in the middle, and any of this vertical line out here represents the phase separation between various species. For example, this vertical line represents the phase separation between solid zinc and aqueous zinc solution. So basically we always use a cell notation, which is technically a shorthand method for describing a galvanic cell or a Voltaic cell. The electrode or this half cell where oxidation takes place is always written on the left, whereas the half cell or the electrode where reduction takes place is always represented on the right. That is, the cathode is always represented on the right. So basically anode on the left and cathode on the right. The cell terminals, if you realize in the previous representation, are always written on the outside. That is, the copper rod and zinc rod were always represented on the outside, and copper rod, instead of undergoing reduction as in the previous case, was undergoing oxidation. Then we would have represented the copper electrode as shown out here, with copper rod being on the left and copper solution on the right. Similarly, if unlike the previous case zinc was undergoing reduction and not oxidation, then we can represent the zinc electrode on the right hand side with the zinc rod being on the extreme right and zinc ions written on the left of it. As I told you all earlier, the salt bridge is represented by 2 vertical lines or 2 vertical bars. Now let's have a look at another example of a galvanic cell. There is a cadmium rod dipped in a solution of cadmium ions, whereas on the other side there is a silver rod dipped in a solution of silver ions. Suppose cadmium undergoes oxidation, then we can always write the reaction as Cd, giving you Cd2 plus 2 electrons. Basically the cadmium atoms from the rod would jump into the solution as cadmium ions, leaving behind 2 electrons on the rod. Obviously that would make the rod negative or electron rich. Whereas if silver ions would be undergoing reduction, then we can write the reaction as Ag plus plus E minus, giving you Ag. So Ag plus ions will go to the rod from the solution, borrow one electron, become silver atom and get deposited on the rod. In that case, since the rod would be losing an electron, the rod would tend to become positive. Now, if the electrodes or the half cells involve a gas as a reactant, then the gas is always adsorbed on an inert material such as platinum. So have a look at this. This is called the chlorine gas electrode. The chlorine gas is adsorbed onto platinum, and hence in this case the platinum is also represented in the cell representation, although it does not take part in the reaction. Similarly, if an electrode involves hydrogen gas, then again it is adsorbed on the platinum plate. Now, if you want to fully specify a voltaic cell, it is absolutely important to represent the concentration of the solutions or ions, and if the gas is involved, then we have to represent their pressures. These concentrations or pressures are always represented in a bracket or parenthesis, as I have shown you all earlier, and as you can see in this particular representation. The copper ion concentration is 1 mole per liter, fluorine pressure is 1 atmosphere, and fluoride ion concentration is 1 mole per liter. Now have a look at this question. The cell notation for a voltaic cell or a galvanic cell is as follows. We need to write the cell reaction for it. So aluminium is on the left hand side, so it is the anode and it will undergo oxidation, whereas copper, being represented on the right hand side, will be the cathode and undergo reduction reaction. So let's see the reactions. The oxidation reaction is Al, giving you Al3 plus 3 electrons, whereas the reduction reaction can be written as copper 2 plus 2 electrons, giving you copper atoms. Now we need to obviously write down the overall cell reaction, and to write the overall cell reaction we have a little problem here, as here there are 3 electrons involved, whereas here there are 2 electrons involved. So we need to balance these electrons in order to cancel them out, and therefore we'll need to multiply this reaction with 2. If I multiply this entire reaction with 2, I'll get the stoichiometric coefficients of aluminium solid as well as aqueous aluminium as 2, whereas 2 multiplied with 3 will make it 6. Similarly, if I multiply this reaction with 3, then the stoichiometric coefficients of copper ions and copper solid will be 3, but the number of electrons will become 3 into 2, that is 6. So both these will have 6 electrons and they will definitely cancel out. So that is what these 6 electrons will cancel each other, and finally the overall cell reaction can be represented as shown. Now I'm sure you all know the concept of potential difference. Potential difference is the difference in the electric potential between 2 points and is measured in volts. Technically, electrical work or electrical energy is represented by the formula charge into potential difference. Now, what is an electrode potential? So when a metal rod is placed in a solution of its own ions, there is a potential difference generated between the two. Now this potential difference between the rod and the surrounding solution is called the electrode potential. So electrode potential is what I have defined out here. It is a difference in the electric potential between the electrode and the surrounding solution. Whereas, what is EMF of a cell? The EMF of a cell is a difference in the electrical potential between the cathode and the anode, or the left half electrode and the right half electrode. At this juncture, I would like to point out that electrode potential is a concept applicable to a single electrode or a half cell, whereas EMF is a concept applicable to an entire cell which consists of 2 half cells or 2 electrodes. Physically speaking, a cell potential is a measure of the driving force of the cell reaction. Now every electrode has its own potential. An electrode which undergoes oxidation easily we can say has a high oxidation potential but poor reduction potential. Now, EMF of the cell, E cell, can be represented as oxidation potential of the electrode where oxidation is taking place plus the reduction potential of the electrode where reduction is taking place. By the way, just a reminder that oxidation happens at the anode. So this would be the oxidation potential of the anode or the left half electrode. Whereas the reduction potential would be reduction potential of the right half electrode or the cathode. Now there are certain tables or charts available which represent only reduction potential, and conventionally an electrode potential is regarded only as a reduction potential and not as an oxidation potential. As a consequence, we prefer to write EMF of a cell in terms of only the reduction potential and not the oxidation potential as shown out here. So it is advisable to write the EMF of the cell by the formula reduction potential of cathode, which is the right half electrode, minus the reduction potential of the anode, which is the left half electrode. So EMF of the cell is E of right half electrode minus the E of left half electrode. So therefore these two quantities, E of RHE and E of LHE, are reduction potentials, and E cell is the EMF of the cell. Now you'll be surprised to know that it is almost impossible to determine the electrode potential of an electrode or a half cell. Why is this so? This happens because you cannot actually measure the potential difference between the rod and its surrounding solution. And hence, to determine electrode potentials of each electrode, we use reference electrodes like standard hydrogen electrode, which have been assigned a certain potential randomly or arbitrarily. So standard hydrogen electrode is one such electrode whose potential is arbitrarily fixed as 0 volts. And at this point of time, I would like to remind you that whenever I use the term electrode potential, I mean it is the reduction potential. Let's analyze these three reactions. Zinc ions picking up 2 electrons, becoming zinc atom. E0 is minus 0.76 volts. The value is negative obviously because zinc would prefer to undergo oxidation reaction rather than reduction reaction, as it is an active metal. Therefore its reduction potential is negative. However, its oxidation potential will obviously be positive and it will have the same magnitude as this, but the sign will be opposite to this one. So therefore the oxidation potential of zinc electrode will be plus 0.76 volts. Similarly, have a look at this reaction. Copper 2 plus ions picking up 2 electrons, becoming copper atoms. Obviously copper being a non-reactive metal has a positive reduction potential. Similarly, your ferric ions are picking up 1 electron and becoming ferrous ions. Here the positive reduction potential value indicates clearly that Fe3 plus prefers to undergo reduction reaction in order to become Fe2 plus. As I told you all earlier that it is the standard hydrogen electrode whose potential is fixed arbitrarily as 0 volts and is used as a primary reference electrode. Let's have a look at its construction. It consists of a platinum electrode onto which hydrogen gas is adsorbed at a pressure of 1 atmosphere, and the platinum electrode is dipped in a solution of 1 molar HCl. So basically the pressure of the gas is 1 atmosphere and the concentration of the solution involved is 1 mole per liter. In that case, the potential of this electrode is given a value of 0 volts. And since we are calling it a standard reduction potential, and since the pressures and the concentration of the species involved are in the standard states, we can call this potential as standard reduction potential, and it's symbolized as E0. So E0 for SHE, which is standard hydrogen electrode, is 0 volt. Have a look at the reduction reaction involved at the electrode. 2 H plus ions from HCl will pick up 2 electrons and become hydrogen molecule. So the bubbles that you all can see out here are generated due to formation of hydrogen molecule. Now, in order to determine reduction potentials of other electrodes, they are combined with standard hydrogen electrode. So for example, if I need to determine the electrode potential of zinc, I will combine it with standard hydrogen electrode and measure the EMF of the cell using a potentiometer. The representation of the cell is shown out here. Zinc ions are in its standard state at a concentration of 1 mole per liter, and H plus ion concentration is also 1 mole per liter. At the anode, that is a zinc electrode, the reaction is zinc atoms becoming zinc ions plus 2 electrons, whereas at the cathode, 2 H plus ions combine with 2 electrons to become hydrogen molecule. So the overall reaction, if we cancel out these 2 electrons here, will be zinc plus 2 H plus ions, giving you zinc ions plus hydrogen gas. Now, if the EMF of this cell is 0.76 volt as found by this voltmeter or potentiometer, then we can easily calculate the electrode potential of zinc electrode for a simple reason that we already know that the electrode potential of hydrogen electrode is 0 volts. So look at this formula. We have seen this formula earlier. E0 of the cell, that is standard EMF of the cell, is E0 of the cathode minus E0 of the anode. That means it is E0 of right half electrode minus E0 of left half electrode. This is the cell representation what we saw in the previous slide, and E0 cell is what we have determined experimentally out here. E0 of hydrogen is 0 and E0 of zinc is what I don't know and I wish to determine. E0 zinc, being the only unknown, can be calculated to be minus 0.76 volts. Have a look at another example. Here I have coupled copper electrode with standard hydrogen electrode. The EMF of the cell is 0.34 volts. So I can easily calculate the electrode potential of copper electrode, keeping in mind that electrode potential of standard hydrogen electrode is fixed as 0 volts. So have a look at this equation. E0 cell is equal to E0 of cathode minus E0 of anode. E0 cell is what we have found out experimentally, 0.34 volts. E0 of anode, which is the left half electrode, is 0 as it is the standard electrode potential of hydrogen electrode. The only unknown being E0 of copper electrode, and therefore E0 of copper electrode turns out to be 0.34 volts. Now this is a table of standard reduction potentials. I'm sure you all will not be able to see it quite clearly. However, I just needed to represent it. It is available in all reference books. And if you look at the middle part of it, then it represents the hydrogen electrode, and it is shown quite clearly out here that it is assigned an electrode potential of 0.00 volts. All the elements below hydrogen in this particular table have a negative reduction potential. That means all these electrodes would prefer to undergo oxidation reactions, whereas all the electrodes above hydrogen in this table have positive electrode potentials and hence are quite capable of undergoing reduction reaction. This is a small part of this electrode potential table, and as you all can see out here very clearly that hydrogen is assigned a potential of 0 volts, and what we calculated in the previous 2 slides is the reduction potential of zinc, which is minus 0.76 volts, and reduction potential of copper, which is plus 0.3 volts. Now let's find out the standard EMF for the following cell. At the cathode or the right half electrode, copper ions is being reduced to copper atoms, and the electrode potential of copper electrode is 0.3 volts. At the anode or the left half electrode, aluminium is being oxidized to Al3+, and the electrode potential for aluminium is minus 1.66 volts. Now to calculate the standard EMF of the cell, what we need to do is take the difference between electrode potential of the right half electrode, which is the cathode, and the left half electrode, which is the anode. So the answer is 0.34 minus 1.66, which is equal to 2 volts.